Yeah, hi everyone. My name is Christian. I work for ARM, and I'll talk a bit about overutilized. We already had a bit of discussion just now. It's very much related to that. So yeah, the overutilized state we have temporarily deactivates EAS essentially. Yeah. So that of course means if we are bad at detecting overutilized, if we're detecting it too often, for example, then we leave energy savings on the table. And it has been reported to be very transient, so it's only there for a short amount of time, switches back and forth, which potentially could ruin task placement stability. And yeah, there was a bit of discussion last year mostly to redefine our overutilized definition, or yeah, the state definition, mostly to make it more topology independent. It's also EAS is evolving quickly there. So EAS was designed for phones, essentially for Android. That means anywhere up to like 10 cores maybe. Nowadays, usually 3 clusters or so. And yeah, laptops look different. So yeah, I'll walk you through the current mechanism and explore some proposals that were either discussed on the list internally at ARM or just by me. So yeah, the underlying idea of CAS, which is what we did when we don't do, or what we do when we don't do EAS, is we have PELT, as discussed by Pierre too, which is we now have like per task utilization signals. So we can, we have a notion of a task potentially fitting on a CPU, and we can place it there. Therefore, we can then sum up a run queue's tasks and get like a run queue utilization and subtract that by the capacity and track that in CPU capacity, which is like the spare capacity then. So how much more can we place on that CPU? Yeah, and the utilization and spare capacity are used for placement and load balancing. And CAS anyway prefers idle CPU, so it spreads those tasks as well. EAS is basically the realization if we have a bit of leeway where to place tasks during CAS task placement, we can choose the most energy efficient. It's basically only wake up based, which means at wake up, we look what's the energy cost and iterate through the clusters essentially. And at the cluster, we only look at the max spare capacity CPU, which is guaranteed to be the CPU where we don't have to raise OPPs for the entire cluster. And also it has the max spare capacity, as in all the tasks there can grow even.
Oh, you're saying the task is enough, or the utilization of the task is high enough, you want you to bump up the frequency for the cluster, even though this is the
right. Yeah, but it's still the CPU where you have to raise the least amount of OPPs.
Yeah,
right, yeah. The util, I usually just say util. It's usually, or it's often dominated by utilized. Essentially, if it isn't, the task is, its compute demand is bigger than it has been in the past. A bit oversimplified, but yeah, utilized is only updated at DQ. So it's like a recent history. And we disable basically all load balance, so we just bail out. That means we do rely on frequent wake up or on reasonably frequent wake ups, because that's when we do our energy decisions. Vincent also mentioned that, and he kind of wants to change it too. That's just the current behavior. Overutilized, similar to misfit. So misfit is when a task doesn't fit on a CPU. We have a threshold, or like a margin. We want to keep 20% spare capacity. So everything over 80% utilization of the capacity is what we call overutilized. It's independent of DVFS, so it's just the CPU maximum capacity in a sense. We also ignore any temporary hardware caps like thermal limits or thermal throttling. This is just, well, just to keep in mind, because even now we don't really have a guarantee that our overutilized definition, if that isn't true now, doesn't necessarily mean we see idle time currently, just because of these artifacts essentially. If overutilized is set, a CAS will kick in and sort of kick some tasks of the overutilized CPUs essentially. There's a few rationales for having this. Originally, it was mostly throughput based. We don't want to have, which is like number 4 essentially. We don't want to do it's a slower NQ path for EAS because we have to do the computation. We don't want to do that when the system is highly utilized. But yeah, more recently, I think the main issue is that we can't trust our pulse utilization signals when we're overutilized. Therefore, making energy calculations on these based on these utilization signals is just wrong. It's basically undefined. But yeah, we also have like increased throughput when it's needed. And anyway, the amount of energy savings, we can save most energy when we have lots of spare capacity, essentially. If we're 80% utilized over the entire system, there's almost no way to place it more energy efficiently anyway.
Yeah, I was curious why utilized is not accurate enough when you're overutilized, because I would think that when you utilized a lot, the decay would be lesser, so it should be close to like the signal should. If you can elaborate, like why is it not reliable? Why is it not reliable?
So if we have like
That was the last talk.
yeah. So if you have co-scheduling or long-term utilization is above the CPU capacity, then you don't have accurate pulse utilization signals because you don't actually know what the computational demand of a task is because you've not given it as much as it wanted to. And anything else is just a guess. Also, util average above a CPU capacity, that's just a guess at this point. If you have on a big CPU, you have every 60 milliseconds, a task wants to run for 8 milliseconds, and you place that task on a 500 capacity CPU, it will look like a busy loop. And util average will detect it as a busy loop and ramp up to 1024. And only when we place it on the 1024 CPU, it will realize it's 512.
So simply speaking, if you have a task that saturates the CPU, it could run faster if the CPU were fast. Okay. Right? So that's the whole thing. So then, but it is not faster, so we can't know how fast it can run.
The only thing that when we consider that the PEL value is not trustable anymore, that's probably where we don't have the same. Not especially you and me in the community.
Yeah. I think it's up for discussion. The 80%, I mean, I did mention that the 80% isn't a strict guarantee that our pulse utilization values are accurate. They could still be inaccurate even though this isn't true. And I think even, yeah.
Yes, indeed, that when you have utilization higher than 80%, it might be better to place a task on an idle CPU rather than placing a task on a CPU which has a high utilization value, because the task is going to run later. So
yeah, but we don't care. Currently, we don't care for that on EAS, basically. But yeah, it has latency, where it has throughput implications. Overutilized is checked and set at tick, task NQ, and load balance. Just keep that in mind. So yeah, this is a Pixel 6. 3 clusters, 4 little CPUs, 2 mid CPUs, and 2 big CPUs. So yeah, I basically just walked through that example by explaining that. But yeah, I've put like the 80% here. Yeah, I'll walk you through one EAS, one of the good examples. So we have, this is a typical EAS placement. The little is much more efficient. So we have 3 tasks, A and B on CPU 0 and C on CPU 1. And you can see how much utilization we think they have. The mid and big are less energy efficient. They are kept idle by EAS. So let's say task A grows. It's currently running. Its util average increased. And now well, here it still fits capacity, but it's over the overutilization threshold. So overutilized will detect this, at least a tick. Cask will kick in and potentially place either A or B, probably actually B because it uses it's lower utilization, so it uses less energy. So you should place it on the less. Yeah, I mean, anyway, that's what could happen. Cask doesn't care. Could either be A or B. Yeah. Now, if B or A, whatever has been placed to CPU 3, decreases its compute demand again, if it's not perfectly periodic, then we could basically be in an endless cycle of CAS and EAS and have these 2 task placements that cycle back and forth. And in the worst case, this could actually mean that we might be better off just sticking with either one. Like either we stick with CAS or with EAS. Even energy-wise, we could run into issues. It's a bit synthetic, but that could happen.
So maybe just with the push callback, the goal normally, if I don't make it wrong, the task B should go to CPU 2 now. Because when the task will try to use when the task is misfit, instead of kicking the periodic load balance, we'll call the find energy efficient CPU and push that normally on CPU 2.
Yeah, I think essentially this is also the motivation for Vincent's patch set, more or less. Just a bit about growing utilization. I've drawn this now, but A grows so much that it actually doesn't fit compute capacity anymore. And now what essentially happens is that A and B's utilization values, we must assume they're inaccurate. We wouldn't have known if they increased compute demand because we couldn't match their compute demand. We don't have accurate utilization values anymore for either one of those tasks to some extent. That's just a fact of life. We don't know utilization or their compute demand if we haven't matched it in the past. This is a laptop, the Apple M1 that runs EAS actually. This is the M1 Pro with 8 CPUs. It has 1 little cluster and 2 big clusters. Can't see the clusters here, they're all the same CPU type. The little is 456, so there's no tiny CPU as the phones usually have. And there's a lot more big CPUs than there's little CPUs, which is interesting. And it goes actually, the Apple manufactures this also in 4+4, 2+8, and 4+16. And maybe you can already see that we're running into a problem here if we have 4+16. Just 20 CPUs in and of itself. If any CPU is overutilized, we're disabling EAS. Could be an issue. Also, if you have many, many little CPUs, same issue. Anyway, the topology looks quite different.
But Vincent's patches addresses, right? The push queue.
Sorry?
So Vincent's patches address that, right? What?
The push callback, I would say that, so in the current version, the condition to push a task is really good. But we can trigger a push more often, and which means that even if at some point a task is not really on the best CPU, or even if the task is changing its behavior, we can migrate that even without wait for the waiting event. We might fix any misplacement or prediction.
But it doesn't change the definition of overutilized.
Yeah.
It's still,
But what's the condition?
it avoids the condition better. Yeah. I mean, basically, we don't avoid overutilized currently in any way because we only have misfit task migration, and the misfit task will have already triggered overutilization. Yeah. Which actually doesn't have to be. We could do a misfit task migration on tick without having overutilized. It's just the same numbers currently, the same threshold. That doesn't necessarily have to be. Yeah, just two workloads. This is running Zoom on Firefox with the video on. One has background blur, where you can't see the background, the effect. That's quite computationally expensive, by the way. One without. I annotated here the FEEX aborted, which is the fine energy efficient CPUs. Just to say how many task placements have we not used EAS because of overutilized. You can basically see without background blur, it's negligible. With background blur, it's about 6% overutilized. And yeah, this is like the distribution of how long it has been overutilized for. It looks reasonably similar for both, except that background blur has like 10 times as much overutilized. But most of the overutilized periods is super short, way below 1 millisecond. So video stream, which is like, I also did YouTube, much higher overutilized, 17%, 16.3. It so reasonably matches task placements. 16.3 have been aborted or not EAS used. So this is the M1. So we have 6 out of the 8 CPUs are big, yet only 7.8% of the overutilized were triggered from a big CPU being overutilized. So it was mostly the littles. And yeah, only less than 1% of overutilized were coming from 2 CPUs at the same time. Yeah, and now just one workload that is really computationally expensive. I don't know if you know like the aquarium where you can render fish. That's basically EAS doesn't make a whole lot of sense there, and we have 50% overutilized aboard most of the FEEX. And it looks very different in the sense that almost all of the overutilized come from big CPUs, and most actually at the same time too. And you can see the distribution as well. Yeah. Yeah.
Haven't you compute the average idle time of the CPU? Because I did that with speedometer on this ATC, and it was amazing that I mean there was more than 60% of idle time.
Yeah, I'll get back to it.
Okay,
Yeah.
that's.
So yeah, 2 workloads on the Pixel 6 as well. One is YouTube, which is really representative of almost all of the workloads, in the sense that EAS uses much less energy, or at least significant amount of less energy. I did play because Vincent originally proposed running fine energy efficient CPU even during overutilized. So I have these plotted as well. And I did find one workload where EAS, even power-wise, is worse than CAS, which is like video scroller, sort of like a TikTok where you load a new video every 3 seconds. It doesn't have any network. It just decodes the video and plays it back. Basically, lots of things going on when you load a new video and not much if you don't. I'll get back to those. Just here, YouTube, 2% overutilized. It looks reasonably similar as what we've already seen on the Pixel. Similar to video scroller, 3.3% overutilized. Yeah, you can see it has like much higher overutilized in the amount of times you overutilize is much higher in the video scroller case. It's more computationally demanding anyway. So here, putting these side to side, and again I have most of the overutilized is coming from the little CPUs. Again, they make up half of this topology. And almost nothing coming from more than one CPU. In Video Scholar, you can actually see the effect that even though we're only 3.3% overutilized, 5% of the peaks are aborted. That means the overutilized periods are where more than average amount of peaks essentially happen, which is what we expect if we expect the workload to be packed in like a certain time frame. What can we do about that? There was one proposal, which is Kais's essentially a very early proposal to make the headroom or the threshold more dynamic. Currently, it's just 80%. And it's quite clever, actually. Basically realizing that 20% of 1024 is still a lot we're leaving on the table, while 20% of 160 isn't. And what Android's OEMs or vendors, phone vendors did was modify this, basically making it for usually like 50% or 60% for the littles and like 90, 95 for the bigs. And the mids are reasonably fine for them. So Kais tried to generalize this, make it upstreamable, not just more magic numbers. So he asked, what if there's one task that runs until the next tick? Would it accumulate enough util average to go beyond compute capacity of that CPU? And that's how he defines the new threshold. It's quite a clever approach. I think it's a bit limited because it's still just one threshold based on utilization. It's just more dynamic in terms of topology. And actually, of course, it could make the situation even worse for little CPUs, in the sense that it takes about, I've had this on a newer version of the slides, I'm sorry. It takes like 35 milliseconds or so on a 160 capacity CPU to reach the 80%. And if we now make this 50%, it only takes like 22 or 24. Yeah.
I think so. One problem is that right now we have the overutilized and the misfit detection, which are the same.
Yeah,
and that's why we want to decrease for the little CPU, because we want to migrate from little CPU quickly. So I think that by decoupling the misfit and overutilized, I would say dump the overutilized to the maximum capacity of each CPU, keep the misfit to the 20% or even 50% for the little CPU. So you migrate much more quicker without spreading everything outside.
Yeah, I think also that misfit and overutilized should be two things, because we have the misfit migration is still a valid EAS migration in the sense that this is probably still the most energy efficient CPU to place it on. I do need, is there any way, no more, I'll just see what comes up. So lingering OU is another idea, because I mean, if it's just 1 millisecond long, and then the reason to reject those utilization values might not necessarily hold because it's only been a millisecond. And pelt can only increase so much anyway during that. They might be negligible. And the other way around as well, technically. I mean, if you match the compute demand of a task only for 2 milliseconds, most of its path has still been inaccurate.
I mean, if we really want to go to the situation where we say we use the pelt only when we are sure that it's accurate trigger, it's quite complex, because as you mentioned, it's not because you're overutilized 1 millisecond that the pelt is screw up, and at the opposite, it can be not overutilized, but the past pelt accumulation has been done when overutilized. So how do we detect that?
Yeah.
That's
I mean, essentially, that's the problem with overutilized and why it's such a global state, because if the compute demand of the run queue exceeds the compute capacity, all of the tasks must be considered wrong. And if we want to deglobalize that state, we essentially would always have to track what tasks have been on that CPU at that time, and they might have disappeared and whatever. I think it's probably intractable.
Yeah, well, the code state itself contains a very queue whether or not it's a reliable indicator. I mean, if your runnable is much higher than your estimate, you're fairly sure it's a dodgy number.
Yeah.
Not always with the utilized, but all the purpose of the utilized. Because you can be co-scheduled, so your util average will not be as fast as you expect. But your utilized remain correct until, I mean, it's really difficult to know exactly. So I would say that trust PEL by default and fix the misplacement. I think that the easiest way for us, I'm not saying that we should always do find energy efficient, but I think we should. As long as we can fix the task placement later on, even if the PEL was not really accurate, we can still fix that then. Otherwise, yeah, that's really quite difficult to say I can trust or I can't.
Yeah. So yeah, this is on video scroller, kind of the problematic workload. We had 7,000, basically 8,000 overutilized on just mainline EAS. If we delay the clearing by 1 tick, 4 milliseconds, that goes down to about 1,000. And if we delay the onset by 1 tick, clear by 2, that goes even lower to 538, while actually not increasing the overutilized time much at all. It does bring a bit of the power back, but it's still worse than CAS. Why is that? So left is just the overall system, right is only the littles, and you can see it reasonably matches. Essentially, EAS stays on the little CPUs with inefficient top OPPs too long, lets tasks grow into that, doesn't migrate quickly, and that actually turns out to be bad for energy efficiency.
And when I see that, we say, okay, we should disable the EAS completely and only rely on the case.
Yeah, but how do you detect the case? Because 99.9, I've been looking really hard to find such a workload. Almost all workloads are either super benchmarky in the sense that overutilized is always set and we don't care anyway, or EAS is so much better than CAS in terms of.
And do you know, maybe you say that, but do you know why the case is better than EAS in this case? What makes it better?
Because we leave the little CPUs so early. And we almost never drive it in the higher inefficient frequencies. Because like the top 4 OPPs, I think, of Pixel 6 are actually less efficient than the mid CPU. And I think even the highest OPP of the little is worse than
because we should have migrated those tasks before, even if they were still runnable. That's the point.
Yeah.
If I understand.
Well, I mean, it could be a solution. I'm just.
No, but that's interesting to see that the case is better than EAS.
Yeah, it is.
Is this one on Pixel 6 or on your M1?
No, that's Pixel 6.
Okay.
We don't have the problem of like inefficient OPPs as much on the M1.
So the problem is that the task gets placed on a sliver, then it grows, and you end up on these high OPPs that are very inefficient instead of pushing it out.
Yeah.
So then the push task set.
Yeah, if it's fast enough, and that's where I think that's where.
But this also drives the OPP. I mean, if it's slow, we're equally slow selecting the inefficient OPPs, right?
Yeah. No, I mean, if it's fast enough, as in if it can react quickly enough. I haven't tried those with your patch, so I can and post the numbers. Essentially, in theory, at least, that should actually fix this particular workload. Could. Another proposal, especially with like the many big CPU topologies, is if we have a bunch of tasks on the first 3 CPUs, and the CPU 3 and CPU 4 are just dominated by one task respectively, and we consider them overutilized because of that. It's a big CPU, it's 1024, it's all we've got. There's no way our pulse utilization signals are going to be accurate. So if we ensure minimal co-scheduling on those two CPUs, we could just not care and let them run and do EAS on the rest. Because yeah, the utilization signals are never going to be accurate on this system. Essentially, we partition the CPUs into trustworthy pelt and non-trustworthy pelt. That's what the overutilized would do then. Historically, I mean, I don't see a reason why we.
I think the
Yeah.
signals for task J and K are very trustworthy.
Yeah, I mean, they are 1024. Yeah.
And that's exactly what they are.
Yeah.
So, we don't have, so for the misfit, we have this case that when the task is on the big CPU, it can't be misfit, even if you reach the highest. Should we do that for the same for the, I mean, if you
Yeah, I mean, we also have to ensure that we don't ruin other tasks by placing it on there, and we probably don't want to do that for we don't want to do full isolation.
No,
Yeah.
no, but I mean, in this case, it's obvious that we are not really overutilized in the sense that the task can get more. I mean,
Yeah, exactly. That would be my point. Historically, that basically didn't matter. If you imagine this happening on a Pixel 6, one big CPU is, or even two big CPUs are completely utilized by one task, then attempting, that's like way more than you can sustain already in terms of power, in terms of thermal pressure. So attempting to do EAS on the rest almost seems silly. While if you imagine you have 16 big CPUs, that could be much more interesting. Yeah, the mainly discussed one was actually basing this on idle time, and it's been just discussed now again. So yeah, if we consider overutilized as a proxy for pelts being trustworthy, then we can base this on idle time. So every CPU should have seen some idle time in the recent past. What does recent past mean? I don't know, probably something on the order of the pelt half-life, maybe twice the pelt half or half the pelt half-life, I don't know, something like that. Essentially, what we're trying to express here is that every task has dequeued at least once in that time. It's a bit easier to track though because it's just per CPU. We could potentially transform this in like a per task called accurate flag. I don't think it's that useful. It's just a thought experiment. Unfortunately, neither one of those is at all compatible with uclump max. It's just that's what uclump max does. You don't see any idle time. You allow more utilization. Then you give it compute capacity. So I don't really know what to do about that because that really restricts our design space in terms of overutilized. And also, it's no longer independent of DVFS. That might be a good thing, it might be a bad thing. That's just what it is. It will, of course, then mean that you're temporarily throttling the CPU, could trigger overutilized, which probably is the correct thing to do, but it's also a bit counterintuitive because you use too much power, you become thermally throttled, and now you make worse task placements in terms of energy because of that, because you've been throttled. It's a bit counterintuitive.
I'm thinking, have you tried to look for, so we have the 5 energy efficient CPU.
Yeah.
Can we use the fact that if we are not able to find an energy efficient CPU, it's probably means that the system is underutilized?
Yeah, I mean the problem is that it's a circular logic, right? Because we use utilization for finding energy efficient CPU, and if we can't trust those values, then I think Contour said, he's not afraid or he's not worried about the case where it returns -1. It doesn't find the CPU it can fit on, but rather it claiming it has found one, while that's not true. Because
but I mean, you always you start to go the find energy efficient CPU. When you have -1, you say, okay, the system is overutilized, so I move back to the overutilized. And then you need to find another condition to say, I'm no more overutilized, so I can go back. Instead of trying to monitor how much compute capacity, if the utilization of each CPU is above, or if you have any idle time, I would say that you are not overutilized if at some point you are not able to find a CPU for a task. It probably means that you will become overutilized anyway because there is no fitting CPU.
If you have a big task at 900 utilization, this task is making this CPU overutilized.
But it should not, I mean, on a big core, that's another thing. I mean, if you have this 900 task, finding an energy efficient CPU should find a big CPU with enough spare capacity. So that should be okay. If he can find, I mean, whatever we do, that would be an overutilized.
So you are suggesting that we go look for an energy efficient CPU always, and if that fails, fall back to something else.
Not, at least if it's failed, move to the overutilized state for a while, I don't know how long. And then you say,
but you could always find a CPU and your utilization signals will still be inaccurate, right? You could have a bunch of relatively small tasks on a little CPU. You overutilize it, and as in you exceeded the compute capacity.
But the find energy efficient will not give you CPU if you overutilize it.
Currently that's only if you have wake-up events for all of these tasks on the CPU regularly. While if the tasks ever grow, you're screwed.
Yeah. Or if you change.
And that's what I try to highlight. That's basically all of the overutilized triggers are this case, as in they come from the little CPU. You know, it's a growing utilization situation.
Okay. But in this case, with the push, we can monitor that more accurately.
Yeah, if it.
I mean, if you try, if you try to move, if the task is misfit or if the CPU becomes overutilized because the task is growing up, using the find energy efficient event, not at work but at runtime, to try to migrate that somewhere else. If you can't, in this case, you are overutilized because there is no good place.
Yeah.
And then we need to find a way to say, okay, we are no more overutilized, which is another thing.
Yeah, yeah. You're still taking the risk of having inaccurate pelt values, which is, I don't know how liberal we can be here. I don't know, it's up for discussion, I guess. Yeah, I'm primarily interested also in what does no longer independent of DVFS mean for x86. I had a slide there and decided to remove it because my test results I couldn't quite explain them all. So yeah, it would be interesting to know if this is something you'd prefer, or if you'd prefer the utilization-based thing. Yeah, just some numbers here on all of the workloads. Essentially, 32 milliseconds of idle absence, if that is what we require. For YouTube, it's the same ballpark on M1. Even the little ratio, that's similar enough. On the Pixel, it looks a bit different. That's still greatly reducing the number of overutilized, and it also greatly, or at least somewhat reduces the ratio. It comes from little CPUs. Yeah, I did want to just also get some input because overutilized and UCount max seems like generally contradicting. It looks like the utilization threshold works, but really it's just a hack. It still means whenever uCloud max is actually active, all of the tasks there have inaccurate pelt values. And whenever we place another task there, then its tasks, the utilization signals become inaccurate too. It's just a fundamental issue. And that really restricts our redefinition of overutilized. I don't know what to do here. If redefining your club max is on the table, which it might not be, making it a true util average cap by scheduling out or blocking, similar to like CFS slotting, but HMP aware would be one solution. Or yeah, am I missing something?
The sum of utilized is also probably one a large trigger of the overutilized state.
Yeah.
Because utilized is the max utilization of the task.
Yeah.
And the max is never the max of all the end task is not
So you
reaching at the same
you
time.
proposed a session in your talk, at least hinted at using some util average. The only issue I have with that is that we're only detecting overutilized when it's already happened. We might get away with that because, as I said, I mean, most of the pulse contributions are still accurate, have been accurate in the past.
Yeah.
But so you say the less is also higher than you say equal periodic task.
Yeah.
Also will be higher than the duty cycle of the task with also an overestimation of the actual duty cycle.
Yeah.
Yeah. So basically, we'll have the situation. What do you think about the proposals, and especially what do you think about the Euclid Max thing? Is what I wanted to discuss. Because it seems to me we basically can't do much here.
Euclid Max is part of the interface, right? It's exposed, so it's used in...
Well, technically it's a hint. You don't. I don't know. I don't think we'd break user space by ignoring it. Technically, but maybe I'm wrong here. Because it doesn't provide any guarantee anyway, currently. It might be effective, it might not be effective, depending on the placement.
True.
It's just a hint.
But it depends on how we design fine energy efficient CPU with Euclid Max task. Like following your proposal or some aggregation or something in between. I think this is... I mean, the patch is still out there, like I said, there is very little really so far. You guys have done something, but I think I don't see a decision there, like which way we go.
Yeah.
You can't need makes sense, but you can't max it's
It has the same issue.
You posit you can't need, but it don't have the same sense actually.
I mean, you can always
Is it used in ADP? Do you know is it used in ADP?
only background task, and it's very static as far as I know.
Don't know. Not
Yeah, I've heard people talk about it, but they can be
It's another level of complexity because I think this is all. There's a vendor hook for Euclid Max as well, so yeah. So,
yeah, it ends up being a how
Exactly.
often too.
so it's very hard to say. Like obviously on mainline maybe nobody's
Yeah.
using it, but
Exactly.
that's the problem with the vendor hooks, right? Like the actual users are maybe not using it, or
Yeah, or even just the user space. I mean, there's no one using Euclid Max for mainline. Full stop.
Drop it. If there's nobody using it on the mainline, drop it.
I mean,
Simple as that.
Android wants it. And
Okay, Android. Not mainline.
I think the only thing is to really engage further, like more
Yeah.
with those Android guys, like in Case, for instance, right?
Yeah.
He can tell us if they can live without it because they have implemented something different in their vendor hook anyway. I think it's called vendor util or so, but it's very hard. Like you said this a couple of times, it's very hard to really understand all the vendor.
We use the vendor.
There was something with vendor, yeah. But
If Android is the only user of it, there's a chance it will get out of control very quickly if somebody starts to play with it and they won't test on Android. Right?
although, if we're being honest, Android also is a really first-class citizen EAS user. Like Android drives EAS.
What I'm saying is this: that somebody, figured out that they would change this somehow, right? And the change goes in like 6:16, and then Android realizes, this is bad. In 2 years later, and then what?
Yeah, I mean that's the situation we're in. Yeah, it's not a nice situation to be in.
Yeah.
But there are more vendors who are running against mainline.
Uclamp Max right now is mainly used to make sure we will never reach higher OPP or big core. It's really a way to say, I don't care really about having the compute capacity that I need because I don't have any deadline.
Yeah,
I don't care how long I will run, but I just want to make sure to not consume power. That's the only reason of Uclamp Max.
Yeah. But ADPF could just disable the top OPPs if it doesn't think it needs it, and if it's running in Fortnite or whatever, you could enable. I don't know. It's just an idea.
The point is that the goal is to say this task doesn't need more than this performance level, and I don't care how long it will run. I just want to make sure I will not burn power uselessly.
Yeah.
But so we can disable OPP, but in this case you need to enable that once you have a task that either you are able to fully partition your system to say the little core will be used only for those background tasks, and that's it. And you can even disable some OPP. I'm not sure. Is it the case that is used by Android? I'm not sure, to be honest.
Prevent task from raising an OPP, you just maybe there's a non-Uclamp Max task and a Uclamp Max task. Run the non-Uclamp Max task first, then the Uclamp Max task. And whenever it will make Uclamp Max task a lower priority class than other tasks, and you will get the same effect.
Yeah.
There's a relation between priority and relation.
I mean, it's another thing. When do we have tasks in Android? It's meaning for Android guys. When you use it to Uclamp Max, do you also increase are you setting the task niceness to 90? Because that's a kind of that's a way also to say that you don't need the CPU only.
I'll just reference it here, by the way, these are the patches I mentioned. ICE is now part of the better managed system response time that John touched upon, and also has a second series that didn't do the overutilized fleek stuff. That's why I linked it. Yeah. But yeah, I'd be interested in some more discussion on Uclamp Max, what's really the use case, and if you can somehow get the mainline also with Intel, with x86 EAS, when that's happening, do we care about it? Is that something you would consider useful? Or what do we do? And also,
He's problematic.
Yeah, agreed.
We just have to make the decision if we need it or not. If it's needed, then we have to deal with it, even though we have inaccurate signals or we can't change overutilize.
We could also keep the interface and just say that whenever there's a Uclamp Max task and there's a non-Uclamp Max task, you just dequeue the task and like this, you have a lower priority, don't burn any energy. You keep the interface and keep the usage as possible. The implementation will be way different.
Anyway, I think we can discuss this over lunch, so
Yeah.
thank you.
Thanks.